Welcome to part 4 of neurons. We've been talking about the resting membrane potential and the potential difference. So what we want to move on to now is, what if the cell is not resting? What if the cell is actually transmitting a message and it's showing current? How is that different? So something has to change in that membrane. I have my little stick man now showing you that it's not resting anymore, it's on the move. So something's happening. But given that we have that ion difference, something has to change in the membrane for that ion difference not to stay at that stable minus 70 millivolts. Something changes. So minus 70 is not maintained. And how do we do that? The change has to happen in the membrane. If you allow that membrane to all of a sudden be permeable to one of those two ions, then they're going to diffuse in or diffuse out. So what happens, we're going to start with sodium. So Na, and sodium is the one that's going to be a change of the membrane permeability to sodium. So all of a sudden, at first they were not allowed in, and now those sodium ions can come in. So let's say this is a graph of membrane potential, and I started out at minus 70 here. And it's resting, and all of a sudden I open those channels and I allow that sodium to come in. So that sodium now is going to come in positive. It's positive ions that are coming in, positive ions that are coming in, positive ions. So it makes sense that this curve is going to go to the less negative. It's going to go towards the zero. It's going to go up, and then if we stop doing that, it's going to come back down again. Or allow other ions to come back in. So this is what happens. The terminology is here, even though this curve isn't really the curve of an action potential. We call it depolarization when it goes away from being so negative. So it depolarizes away from a pole and it becomes more positive. And it's going to repolarize when it goes back down to being more negative. And then if it were to overshoot, we would call it hyperpolarization. So let me show you what it really would look like. If you had that graph where you have millivolts, and we started out here at the minus 70, every time I click this, it's going to change. And we're going to make it around 0 here, and we're going to make it around plus 30 millivolts up at the top here. So here's my graph, where I have minus 70, nothing's happening. I'm here at resting potential. And all of a sudden, I open, for some reason, I allow those gates to open and sodium is going to pour into the cell through the membrane. Sodium's positive, so this is going to come up. So if that sodium channel's opened, I'm going to come up. How far am I going to go? Does it keep going? Yes, it keeps going. It keeps going until about plus 30. At which time that channel stops. I'm going to change my pen here. And then it's going to change, and those channels are no longer open to sodium. But what happens is the potassium channel opens. And if you remember, potassium was mostly in the inside of the cell, so potassium instead is going to move out. So if positive ions move out of the cell, does it make sense to you that it would start to become more negative again? Because those positive ions are leaving. And if they're leaving, then I'm going to get more negative. And these potassium channels are open, allowing the flow of that potassium out. And what happens is something like this. It takes a bit to go back to normal. So this is what the action potential curve would look like. It's going from this region here, where sodium has come into the cell, stopped in the middle. Let's make a line there. And this is the region where potassium has been able to exit the cell, bringing it right back down again and overshooting a little bit. Do you notice how I overshot there? So by overshooting then, this is going to be the region of, I'm just going to put an H, hyperpolarization. So this region, let's go back to black, is, I'm going to put D here, depolarization. This region is repolarization, and hyperpolarization as it overshoots and then comes back to resting membrane potential. Let's see if it does this without changing the slide on me. Okay. So this all happened because there was an increase in the membrane permeability to sodium. These words here, I usually go over them again and again and again, and I say it a million times. There's an increase in the membrane permeability to sodium. If all of a sudden, if this were the inside of the cell and that those gates open, channels now open, and now sodium that's positive is going to be able to pour in and pour in until a certain, not forever, here a gate's closed. So open for a certain period of time. How long is that period of time? Didn't really show you in the last one what this here is. And this is about 3 milliseconds. Very fast, very fast. But it will close again. So by having an increase in the membrane permeability to sodium, then that sodium is going to come in, making the inside of the cell much more positive than it was. And then there's a reversal. The repolarization has the return of the membrane potential because potassium that's also positive will go out, and it starts to restore that negative potential inside the cell. What if too much of the potassium flows out? That's what we're going to call hyper. Hyper is too much. Hyperpolarization. That increase in permeability to potassium allows too much of it to escape the cell. So it drops below the negative 70 millivolts, maybe negative 80, maybe 90, until it comes back in again when more of that sodium exits. Excuse me, when more of the sodium comes in. So what changes the permeability of the membrane? Well, what was it that all of a sudden made it so that there was a change in the membrane permeability to sodium? Well, it depends. We talked about this before. It could be current, it could be voltage that hit it, right? Some other cell that was bringing current and zapped it. And now it's subject to that voltage that opens those sodium channels, and that sodium is going to go in. So it could have gotten zapped. And you can do this in a lab also, where you would just get a little voltage probe and hit that neuron with a little bit of voltage, and that's what's going to happen. Sodium's going to pour in because those channels are going to open. So that's how you could do it, with current. How else can you change the membrane permeability? With hormones, or a chemical, a neurotransmitter that comes to the cell and changes the behavior of the cell, and all of a sudden it opens a sodium channel, and boom, you have an action potential. What else? Pressure. Stretch or pressure, just pressing on a nerve, a neuron, just pressing on it, will cause this. Hard to imagine when you're thinking of the body. How does that happen in the real body? And the example I always give is of the bladder. You know, the bladder is empty and it's fine, nothing's happening, and all of a sudden it fills and the pressure starts to build in the bladder, and then there's a message sent, an action potential message sent to the brain saying, need to void, correct? And how did that happen? Well, that message came because there was enough pressure in that organ that pressed on those neurons. What else? Current, hormones, pressure. And actually temperature, if there's pressure at a higher temperature or hormones at a higher temperature or current at a higher temperature, is going to increase that response. So that's also triggering. Not, it'll aid the triggering of these of 1, 2, and 3, but also on its own, it can create an action potential. So when your temperature starts to rise, what do? You start to sweat. So those glands have to open up. And what's the signal to open up? Temperature, heat. And it's going to open a sodium channel. Sodium comes in, you get an action potential. That action potential says, okay, release water. And you start sweating. So these are going to be in your body regulating how these action potentials get triggered. I hope that's super clear. And that's where we stop. Thanks for listening. That's the end of part 1 of neurons.